Welcome, everyone. I am absolutely thrilled to have you here for this explainer. Today, we are tackling something that I see causing absolute, unnecessary panic in the exam hall: mathematical notation. We are specifically looking at the Cambridge IGCSE and O-Level Additional Mathematics 0606 syllabus. But listen, right off the bat, I need you to completely shift your perspective. I want you to stop thinking about this as intimidating math. Instead, think of mathematical notation as a foreign language. It has its own precise vocabulary, its own punctuation, and its own grammar rules. Think about two typical students taking this exam. Let's call them Alex and Sam. Now, Alex is the kind of student who overloads on raw mathematical facts but completely lacks analysis. Alex memorizes every formula but freezes when the question uses a weird symbol. Then you have Sam. Sam rushes. Sam reads the question too fast and completely misses the subtle requirements hidden in the command words and symbols, losing massive marks in the process. Today, we are going to decode this language together, step by step, so you don't make the mistakes that Alex and Sam make.
Be honest with me for a second. When you open up a past paper and you look at a complex string of calculus, or maybe a densely packed vector equation, does it look like an alien dialect? You literally wouldn't be alone in thinking that. This is where Alex starts sweating and Sam just guesses and moves on. Cambridge exam papers intentionally use these dense symbols to test your confidence and your precision under pressure. Seeing a jumble of Greek letters, tiny floating numbers, hats, and exclamation marks can trigger an instant stress response. It looks like a completely different language. But I promise you, by the end of this explainer, you will be able to read these exact expressions fluently. Understanding these symbols is your ultimate exam strategy. It's going to save you precious time, conserve your mental energy, and stop you from losing silly marks. It really is just a matter of learning the vocabulary.
All right, let's quickly run through our translation manual for the 0606 syllabus. This is our blueprint for today. First, we're decoding basic punctuation. Then, we move into functions, or what I call complex sentences. Third, we'll tackle the calculus vocabulary. Fourth, we dive into special dialects like vectors. And finally, we'll put it all together for total fluency. Let's get right into it. Section 1, Basic Punctuation. We're going to explore relationships and operations, the absolute foundational building blocks of your exam answers.
In English, we use commas, periods, and conjunctions like and or but to connect ideas together. In mathematics, we use a foundation of symbols to establish basic relationships and operations. These are the verbs and the conjunctions of our mathematical sentences. Look, we are moving completely beyond the simple equal sign here. An equal sign is great, but it really lacks nuance, and nuance is what gets you the top grades. Look at the three horizontal lines on your screen. That doesn't just mean equals, it means identical to or congruent to. It's a much stronger statement. The squiggly lines, that translates to approximately equal to, which is absolutely crucial when you're rounding in your final steps. A single tilde tells us something is distributed as, which you'll see in statistics. Adding an equal sign under that tilde means is isomorphic to. And then, look at that little fish-like symbol at the bottom. That translates directly to is proportional to. If a question asks about proportionality and you immediately throw down an equal sign without a constant, an examiner is going to dock you points immediately. We aren't even doing calculations here. We are just reading nuanced relationships properly.
Now, these next symbols brilliantly illustrate the logical flow of mathematical arguments. Instead of just stating random facts on a page like Alex does, math lets us actually show how one idea causes another. The right-facing double arrow means implies, the left-facing one means is implied by, and when you have an arrow pointing both ways, it means the statements imply each other. They are mathematically equivalent. And of course, our sideways figure 8 at the bottom is the universal symbol for infinity. These arrows are the connective tissue of mathematical proofs. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now, because mastering these exact logical flows is exactly what we teach every single week.
Okay, let's define some specific operational vocabulary. When you see a variable, let's say a, bracketed by two straight vertical lines, you are looking at the modulus of a. I cannot tell you how many times I've seen students completely ignore these lines. Think of it as the absolute value. It's the magnitude without any regard to the sign. It's always positive. Right below that, we have our roots. The classic square root symbol gives us the non-negative square root of a, but you need to pay really close attention to the difference here. If we pop a little n onto the ledge of that symbol, it changes the translation entirely. It is no longer just a square root, it becomes the real nth root of a. If you misread that little n, your entire calculation from that point forward is going to be completely wrong.
This next one is fun, but it trips people up. The crucial point here is that an exclamation mark isn't math shouting at you excitedly. In our language, an n followed by an exclamation mark is read as n factorial. It is a compact, elegant way to represent multiplying a descending series of integers. 5 factorial is 5 times 4 times 3 times 2 times 1. Simple, right? And that factorial vocabulary is immediately put to use in the expression right below it. Notice how the binomial coefficient, which we read as n choose r, is calculated using those exact factorials. It's n factorial divided by the product of r factorial and n minus r factorial. If you don't know what the exclamation mark means, you literally cannot even begin to unpack a binomial theorem question.
Section 2. Functions. This is where we start crafting complex sentences in our mathematical language.
This is where the magic happens. We start mapping inputs to outputs. We are no longer just making simple static statements. We are describing ongoing dynamic processes. On the left, we have our standard function mapping. You can read f of x as the value of the function f at x. You might also see it written with an arrow featuring a small vertical base that translates precisely to the function f maps the element x to the element y. But look at the right side of the screen. Look at that -1 exponent. In this context, it does absolutely not mean 1 divided by f. This is exactly where our rushing student Sam loses marks. Sam sees a negative exponent and flips it into a fraction. Don't do that. In function notation, that -1 translates specifically to the inverse function of the one-to-one function f. It's the linguistic equivalent of hitting the rewind button on your calculation. It undoes the original function. We can even chain these concepts together into what we call composite functions. When you see g of f, you are looking at a composite function where the output of function f becomes the immediate input for function g. Therefore, g of x is identical to g of f of x. It's literally like a mathematical assembly line. And here is the golden rule that examiners love to test. You always work from right to left. You plug x into f first, get that result, and plug that result into g. If you read it like a normal English word, left to right, and do g first, your answer will be a disaster. The notation explicitly tells you the order of operations if you know how to read it. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Welcome to Section 3, Calculus Vocabulary, the Math of Change.
If basic algebra is a static photograph, calculus is a high-speed video. It is a vocabulary dedicated entirely to the mathematics of change, motion, and accumulation over time. But before we can take a derivative or calculate an integral, we need to understand the foundational building blocks of calculus notation. Look at the first bullet on the screen. Lim, followed by a little arrow pointing from x to a. We read this as the limit of f of x as x tends to a. It's about approaching a destination. Below that, we have the Greek letters, capital delta and lowercase delta. When you see these attached to an x, like delta x, it simply translates to an increment of x. It just means a tiny, perfectly defined chunk of change.
Now I want you to watch how the vocabulary of a derivative evolves. This is super important. Start at step 1. We have our original function, just y or f of x. Now look at step 2. We can express the first derivative with respect to x as either dy over dx, or we can use a little prime mark, f prime of x. Step 3 shows us how to scale this up. If we want the nth derivative, like a second or third derivative, we use superscript n's written as d to the power of n y over dx to the power of n, or f double prime, triple prime, and so on. But watch closely at the bottom. This is the trap. If we are taking derivatives with respect to time instead of x, like in mechanics or kinematics questions, our vocabulary changes completely. We use dot notation. An x with one dot on top is the first derivative with respect to time, which is velocity. 2 dots is the second derivative, which is acceleration. If you use dy over dx in a kinematics question, the examiner knows you don't really understand the language.
Integration has its own critical grammar rules, and the crucial point is comparing these two specific notations. The tall, stretched-out S shape is our integral sign. On the left, we have the indefinite integral of y with respect to x. Notice how clean it is. There are no numbers attached to the top or bottom of the symbol. When you see this, you must add your constant of integration, plus c, at the end. But look on the right. We have a definite integral. The tiny a at the bottom and b at the top are your boundaries. It translates to the definite integral of y with respect to x between the limits x equals a and x equals b. This is when you are calculating a specific area and you don't need the plus c. Missing those tiny letters a and b changes your entire approach to the problem.
Section 4. Special dialects. Just like any deep language, math has regional dialects for specific topics: trigonometry, logs, and vectors.
Just like a chef or an architect uses specific, highly technical jargon, we use distinct notations for specific mathematical terrains. Let's decode the logarithm family first. The specific notation used here instantly tells us the base of the log without the examiner having to write it out every single time. If you see ln x, that is the natural logarithm, which means it uses the base e, the exponential function base. If you see lgx, or log 10x, that's the common logarithm using base 10. And if the base is variable or unknown, you'll see a little subscript letter, like log ax, meaning logarithm to the base a of x. Alex often tries to treat all logs the same, but ln and log behave very differently when you start differentiating them.
Now let's look at trigonometry, or circular functions. On the left, we have our standard toolkit: sine, cosine, tangent, cosecant, secant, and cotangent. You are likely very familiar with these ratios, but look at the right side. Similar to the inverse functions we saw earlier in algebra, circular functions have their own -1 inverse counterparts. So sine to the power of -1 translates strictly to the inverse circular function of sine, allowing us to work backward from a ratio to an actual angle. Once again, do not confuse this with the reciprocal. Inverse sine is not 1 over sine. 1 over sine is cosecant. Getting those two twisted is a classic exam error.
Vectors are a place where notation is absolutely everything. In vector geometry, the simplest typographical changes completely alter the meaning of the concept. A bolded lowercase a or an a with a squiggle under it just means the vector A. Capital A, capital B with an arrow over it specifically means a directed line segment from point A to point B. The direction matters. But look at the third one on the list. If you put a little circumflex or a hat on the A, it specifically translates to a unit vector in the direction of A. That means its length is exactly 1. Furthermore, I and j aren't just any random variables here. They are exclusively reserved as the unit vectors for our horizontal and vertical Cartesian coordinate axis. And finally, if we put our vector inside those straight absolute value bars we learned earlier, it now translates to the magnitude of vector A. It's asking for the length, not the direction.
We've made it to Section 5, Fluency. This is where we put it all together and prove that you've mastered the notation.
Incredible work! Take a deep breath. We have officially translated the key categories of the 0606 Additional Mathematics syllabus. We've moved from intimidating, scattered, alien symbols into clear, structured, and readable concepts. Looking back at the complex, dense text we might have started with on slide 2, you can see that it's just not scary anymore. If you see a limit sign, an absolute value bar, a superscript n on a derivative, and a double-sided arrow, you don't panic like Alex, and you don't rush like Sam. You pause, you decode, and you just read it left to right as a perfectly logical English sentence. The limit as x tends to a of the modulus of the nth derivative of f of x implies. You are quite literally reading the underlying language of the universe right off the page.
And that brings us to the end of our translation manual. By mastering this notation, you aren't just memorizing arbitrary symbols. You are unlocking the ultimate blueprint for advanced problem solving. You now have the vocabulary to properly describe infinity, to track a moving object through time using dot notation, and to map multidimensional space with vectors. Being able to read these rapidly and accurately in the exam hall directly translates to speed, to confidence, and ultimately to higher marks. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Thanks for joining me on this explainer, and keep exploring.